Good morning, good afternoon, good evening. Welcome to Flat Earth School, the school that is around us 24/7 since the beginning of existence. I'm Mitchell from Australia, just a student like the rest of us, here experiencing and learning on our beautiful Flat Earth School. It is the best teacher you could ever hope for. If you enjoy my work, if you want to support my work, please follow the links in the description below. There's links to my PayPal, Patron, ROKFIN, and also links to purchase my wife's book, ABC Pregnancy, online. I appreciate all the support. You guys are awesome. Mike Zunich says in the chat, no bendy lines allowed at Flat Earth School. Correct. When we're doing something like triangulation, no bendy lines allowed. And this show is called Triangulation using a Sextant, because that's absolutely what we do. Now, we've had a recent claim that we're not using triangulation when using the sextant or celestial navigation. Apparently that's not what we're doing. Apparently we're using trilateration. And we're going to go through the difference between triangulation and trilateration, because it is vastly different. Before we get started, I'll just go through the chat. You guys, thank you for turning up. True Seeker, PJ Crookshanks, hey, Snowbirds, Mike Zunich, Nurparatados, how are you? Ben Firth, good evening. Yes, may God bless each and every one of you. Thank you for being here today, because it will be, this week, I'm going to be going pretty hard on the use of a sextant. And my special guests on Friday, or Saturday if you're in Australia, will be Brian's Logic. And we will be absolutely pummeling any claim that the sextant is being used on the globe, any claim that the sextant uses trilateration, any claim other than what the sextant is actually used for. Alvin Wilson, yes, good morning. Going pretty well, PJ Crookshanks. It's a great day, a great time to be a flat earther. Bill Nye, the Science Denier, says, what up, y'all? I'm new here. Well, we picked a great show to be new on, because we're going over triangulation using a sextant. Notice it doesn't say trilateration using a sextant. Now, why is it that when we're going through information to do with the sextant, none of the information comes up with trilateration? Is it because we don't use trilateration? Why do all the references say we use triangulation? Well, I think we need to go into what these terms actually are. I'm going to pull up some references here. So what have we got? This one here. All right. So we'll start with trilateration. This is trilateration versus triangulation. And it's going to become very apparent in a second what we're actually doing with the sextant. So this is triangulation versus trilateration. Right, so when taking indoor asset tracking, when talking about indoor asset tracking, it's important to keep in mind that it's made up of a loosely woven group of technologies. Why are we talking about technology here? The sextant isn't technology, the sextant is an angle measuring device. So each of which can calculate position using one of two methods, triangulation or trilateration. The two are distinct in important ways, even though they can both theoretically contribute to a single indoor positioning solution. Why are we talking about technology? Yes, we're talking about positioning, but let's go into what is triangulation. Triangulation is a method for calculating positions that relies on a known distance between two measuring apparatuses. Two measuring apparatuses. What are we doing when we have a sextant? Do we have two measuring apparatuses? No, we have one measuring device and the measured angles. There we go, the measured angles. So that's at least that's a bit to do with the sextant because the sextant is an angle measuring device. But why is it saying we need two measuring apparatuses when the sextant only uses one? Might this be talking about something other than using the sextant? So this works using angle side angle triangle congruency theorem to find the location of an object. So do you think we're talking about the sextant here? It's going to become very apparent what we're actually talking about when this conversation comes up about triangulation versus trilateration. So what is trilateration? Trilateration is the more common method for positioning calculations. Why are we doing calculations? We're doing physical measurements when using the sextant. So trilateration uses the known distances from at least 3 fixed points in 2D space or 4 fixed points in 3D space, as if on the surface of the Earth. So there's the claim that we have a 3D space on the surface of the Earth, begging the question. Not saying anything about a globe, but alluding to it. So to calculate the position of an object, trilateration works by finding the intersection of a series of circles. Well, that kind of sounds like what we're doing with a sextant. But hang on, using known distances? Do we know the distances when using the sextant? No, we have to derive the distances. We don't know the distances. All we know is the angles. That's what we know. So triangulation and trilateration process in practice. In the asset tracking space, could this be talking about something like GPS, like technology, like cell phone towers? Obviously, you're gonna want to point to satellites, but that's a begging the question fallacy. There's no proof that we have an orbit of anything. There's no proof that we have satellite. Definitely proof that we have ground-based towers. So this triangulation versus trilateration conversation is all to do with something with technology. Why are we talking about technology when we're using an angle measuring device, a physical thing that... Let's go to the next one. Trilateration. How distance measurements help to work out calculation. What about angles? Why are we not using angles? That's what we're doing with the sextant. So triangulation projects lines of unknown length. Yep, that's what we're using with the sextant. We don't know the length. Along known angles. There we go. Known angles. That's what we use with the sextant. We know the angle. We're measuring the angle. So triangulation uses angles. So as long as there's more than one reference point, we can identify the location of a new point. Why are we using more than one reference point? We're using one sextant. We haven't got more than one location. It says here, so if we know point X is located at angle 450 from point 1, and then why are we talking about different positions? We got one sextant. Why is this conversation with trilateration versus triangulation always using more than one position? We only ever have one position when using this sextant. We don't call up somebody somewhere else and go, oh, see that star over there that I shot 45 degrees to it. What do you get? Do you get 45 or you get something? Oh, you get something else? No, we don't call other people when using the sextant. We do it by ourselves. And so it goes on to trilateration, works in a similar way, but uses distances rather than angles. So trilateration doesn't use angles. Isn't the sextant a angle measuring device? Why is it saying that it's using distances? That's not what we're doing with the sextant. We're using angles. So the other major difference is that when you trilaterate, you need a minimum of 3 reference points rather than 2 to narrow down the search of a location. So you can see here in the diagram, known length. We don't know the length. All we know is the angle. Now these things here, they look like angles of equal altitude, don't they? They look like that's what could be happening when using trilateration. But this is assuming we already know the distances. See that? Point 1's got distance, point 2's got distance, point 3's got distance. We don't know these distances. All we know is the angles. That's what the sextant is. That's what celestial navigation is. Using angles, triangulation, to find your position. So how does GPS receivers work? Trilateration versus triangulation. There's that GPS. Why does the conversation get brought up about GPS? Why can't we use the conversation when using the sextant, trilateration versus triangulation? Can anyone find me a reference? Triangulation versus trilateration to do with the sextant? Why is it GPS receivers? So here we go. We've got 3 satellites, 1, 2, and 3. Yeah, begging the question that there are 3 satellites. I'll assert that they are ground-based towers. But let's not digress from what it says here. So they look like areas of equal altitude, don't they? And here's the thing. When using trilateration, you're actually using distances from something like that satellite or ground-based tower, and it's making a radius. So we've got a distance, we've got a straight line. And where those straight lines, those distances meet, is where your fix would be. But unlike using the sextant, you're in the middle here and you're looking at 3 stars. So if you're when using the sextant, imagine those satellites are stars. So you're in the middle there and you're looking at the angles to those stars. So satellite 1, we'll call that star 1. So star 1, we're looking at an angle to that, measuring it with the sextant. Star 2, doing the same. Star 3, doing the same. We've got areas of equal altitude. When using satellites, it's the other way around. When using GPS, it's the other way around. It's all coming from the satellite out to the point. It's not the point to the satellite. That's why trilateration has it all backwards. We don't use trilateration with the sextant. We use triangulation. So GPS receivers use trilateration. If you ever wonder how GPS receivers work, they use a technique called trilateration. So despite how GPS receivers are often confused with triangulation, which measures angles only, there it is. Triangulation uses angles. So GPS receivers don't use angles at all. So why are we talking about something that doesn't use angles? Because that's what we're doing when using the sextant. It's an angle measuring device. So trilateration involves measuring distances. Where's the angles in trilateration? Right there, it says trilateration measures distances, not angles. So how can we use trilateration when using the sextant? It's a non sequitur. Trilateration measures distance, not angles. What does the sextant do? It measures angles. So we're absolutely not using trilateration when using the sextant, are we? Once again, we've got the satellites. They're broadcasting a signal from the satellite. The star's not broadcasting. When we're using a sextant, the stars aren't broadcasting anything to us. We're looking from our point to the stars. It's totally opposite when using trilateration. And where the circles here, GPS circles, intersect, that's where we are. But we're not at these 3 points. We haven't got 3 reference points here. We've got 3 stars that we're shooting at an angle to, And as I keep saying, the satellites are giving a signal from those points outwards. They've got known distances. And when they meet, that's where you are. That's how GPS works. And it's definitely not on a globe, as you'd see here. 3 spheres? Here we go. Triangulation. Measures angles, not distances. There we go. That sounds a bit more familiar when using the sextant, doesn't it? Triangulation measures angles, not distances. So on the other hand, surveyors use triangulation to measure unknown distances. That's exactly what the sextant does. They do this by establishing a baseline length. There we go. We've got a nice flat baseline. Now keep in mind this is surveyors. So obviously if you're using something like a total station theodolite, we're measuring things on the ground here. It's nothing to do with the celestial bodies above our heads. So although surveying is very similar, and although surveying needs that flat baseline, 3 straight lines, it's not quite the same as using a sextant, but surveying absolutely also proves a flat Earth. So from each point of the survey, the surveyor measures angles of distant points using instruments like theodolites. When we know the lengths and the angles, triangulation determines the distances by forming triangles as shown in the diagram above. And once again, we've got point 1, point 2, point 3. So we are not using those 3 points when using the sextant. We have only got 1 point, 1 reference point that we're trying to find. We're trying to find our 1 point. And we're using other things like the stars around us to triangulate our position. So another couple of things on trilateration before we get into what triangulation is and how we use it with the sextant. So GPS again, trilateration. GPS can be compared to trilateration. So both techniques rely exclusively on the measurement of distances to a fixed position. So distances to the fixed position, we're already at that position. We're trying to find that position. Why is there more than one reference coming to our position? So one of the differences between them, however, is that the distances, called range in GPS, are not measured to control points on the surface of Earth. Instead, they're measured to satellites orbiting in nearly circular orbits, begging the question, 20,000 kilometers above Earth. Why do we need satellites orbiting? Why do we need to beg the question? Why do we need to go into this with trilateration? We're not using satellites. We're using stars when using the sextant. So trilateration all has to do with known distances. The sextant all has to do with known angles. Very, very different. So these are some good slides here. Trilateration. Length measured all sides. So length measured all sides angles computed by cosine rule. So trilateration is the method in which the lengths of all sides of a chain of triangles, polygons, or quadrilaterals, or any combination of them, are measured with what? With an electronic instrument. Their angles are then computed. No, we've already got the angles when using a sextant. So why are we talking about computing angles? See, that's the difference here. Trilateration has to rely on calculations to get the angles, but we've already got the angles using the sextant. That's what the sextant is, an angle measuring device. We use the sextant to look at the stars, and we measure the angle from our observer point to the stars. So why is it saying we're using an electronic instrument in trilateration? Is it because we don't use trilateration with the sextant? So angles of the triangles and the coordinates of their vertices are determined by trigonometric computations. So although trilateration still uses trigonometric computations, it says in contrast to triangulation, it does not involve the measurement of angles in a field. Why are we talking about trilateration when using the sextant? It specifically says we do not measure angles when using trilateration. That's what we're doing with the sextant. We measure angles. So trilateration has nothing to do with the sextant. This is trilateration. You've got a known position. And you've got known distances. And then you're calculating the angles. With the sextant, we know the angles. We're measuring the angles. We don't have to calculate the angles. It's totally backwards with trilateration versus triangulation. So triangulation in its principles, it is the process of measuring angles. There we go. That sounds a bit more like the sextant, doesn't it? It's the process of measuring angles of a chain or network of triangles formed by stations marked on the surface of Earth. That's what triangulation is. If all three angles and lengths of one side of a triangle are known, then by trigonometry, the lengths of the remaining sides of the triangle can be calculated. So when using a sextant, we have to calculate the distance. We don't know the distance. That's what trilateration relies on, knowing a distance, already having the distance, and then calculating the angles. It's the opposite for triangulation. Triangulation knows the angles and then calculates the distances. Totally opposite. Some examples of surveying. So in the conversation of trilateration versus triangulation, why does the sextant come up? So we've got surveying. Here we go, triangulation versus trilateration. This is a good one. I think this is a bit bigger here. Triangulation. Number one, the angles are measured in triangulation. Yep, that's what we're doing with the sextant. Trilateration, on the other hand, number one, all sides are measured in trilateration. Nope, not measuring sides in with the sextant. Triangulation number two, distance of the baseline is measured. That's what we need to do with the sextant. Number two, with trilateration, azimuth of the initial line is measured. Nope, not doing that with the sextant. Number three, the triangulation, some check baselines are also measured to control scale error. Number three, with trilateration, some check angles are measured to control azimuth error. Yeah, so we don't know the angles when using trilateration. We absolutely do know the angles when using triangulation with the sextant. So triangulation, number five, intervisibility between stations is essential. Number five, for trilateration, for small areas, it is possible to measure the distances without intervisibility. Not really anything to do with the sextant. Number six, for triangulation, there are more internal checks in comparison with trilateration in the same geometric figure. Number six, for trilateration, there are less internal checks in comparison with triangulation in the same geometric figure. Number seven, triangulation, the side lengths are computed on the basis of measured angles, applying the sine law. So we've got measured angles. Then we have to compute the length of the sides. Sounds like using the sextant, measured angles. But number seven, with trilateration, the angles are computed on the basis of measured lengths, side lengths. So you already know the lengths, and then you have to compute the angles. Why do we need to compute angles when using the sextant? We already know the angles. So that just highlights the difference between triangulation and trilateration. So now that we know what trilateration is, and get rid of this, we can go on to what triangulation is. Hey, 10th man, see you in the chat here. Good to see you. Michael Khan, how are you? All good stuff going on here. Level up. Betty, how are you? Hope everyone's happy and healthy today. Enjoying this presentation on what trilateration versus triangulation is. So I think we've figured out what trilateration is. It's using distances, isn't it? Using known distances. And then you have to compute the angles. Why are we doing that with the sextant? We're not. We're using the known angles with the sextant. All right, so let's go into screen share. Let's go into triangulation. Hey, Owen, good to see you here, mate. Let's see, where is, there we go. All right. Hey, Quantum Racer, how are you going, mate? Yeah, show a curve to Jason Paulus. Exactly. All right, so what is triangulation? Here we go. From Noah. Navigation at sea. A matter of triangles. So once a transit, right here, once a transit is properly set up and aligned, its scale markings can be used to accurately determine distance and direction or range and bearing. To a sighted target, making transit measurements from two perspectives of known distance apart. The measurement of dual range or dual bearing measurement for locating a third point. The point of interest is known as triangulation. So that's terrestrial-based triangulation. So we go down a bit when using the sextant here. For centuries, Marinus has also used a form of transit called a sextant and a triangulation method using stars, sun and moon as benchmarks. Even though these celestial bodies move across the sky. So we're actually using triangulation with the sextant. Isn't that funny that the sextant never comes up when looking into what trilateration is? When we're looking at what triangulation is, we're getting things about the sextant. So a reference here from sciencejrank.org on the sextant. The optical instruments called sextants have been used as navigation aids for centuries, especially by seafarers. Its simplest form, a sextant consists of an eyepiece and an angular scale called the arc fitted with an arm to mark degrees. Yep, that sounds like what we're doing with the sextant, isn't it? Angle measurement. By manipulating the parts, a user can measure the angular distance between two celestial bodies, usually Earth and either the sun or moon. The observer can thereby calculate his or her position of latitude by using trigonometric operation known as triangulation. So that's just with one observer. That's what we're doing with the sextant. Remember, trilateration relied on 3 reference points, 3 towers, 3 satellites, all transmitting a signal. And where those signals intersect is where your position will be. Well, this is the opposite, isn't it? When using a sextant, we've only got one position. And that's what we're trying to find here. And we're using 3 reference points like the stars from the sextant, from the observer point outwards, not from the reference points inwards. That's what trilateration was using. That's what GPS uses. That's not what the sextant does. The sextant is trying to find your position by measuring the angles to the reference points, not the reference points measuring distances to the observer. Triangulation, that's what we use with the sextant. So how did sailors navigate by using the stars? If a navigator knows where a star is located above the Earth, he can determine his distance from that particular subpoint. So we don't know the distance here. Remember with trilateration, we know the distance. So he needs a tool to measure the angle between the stars and the horizon, like a sextant. Isn't that handy? The sextant is an angle measuring device to measure the angle between the stars and the horizon. Now he has a line of position. When repeated, he can triangulate his position. That's the celestial fix. And then it goes into most sailors use multiple navigation methods like GPS, chart plotting, compass, radar, echo sound. What if you just got a sextant? Triangulation. So this is to navigate safely when lost at sea using nautical chart, a sextant and a compass. Let's consider 3 main points to take into account here: the stars, the skyline, and you. That sounds like three lines, doesn't it? Using a sextant or another angle measuring device, so the sextant's an angle measuring device, you can use these 3 different points to triangulate your position, your location. The sextant, for example, uses the horizon and a celestial body in the sky in order to determine where you are. There's a very easy guide on how to use this here. So the sextant, once again, using triangulation for your location. Why, when we look into trilateration, why does it not come up with anything to do with the sextant? It's because we do not use trilateration with the sextant. We do not use known distances with the sextant. We have to derive that. We have to calculate that. We know the angles. That's all we ever know when using the sextant. And that's the difference. The globers like to bring up trilateration in this argument because they want to take us away from the angle measuring device. Like I've been talking about, trilateration uses known distances and has to calculate the angles. Why are you calculating angles when using a sextant you already know the angles? That is just the deception they're trying to push here. They're trying to push celestial navigation using the sextant. They're going to try and push the use of the sextant out of the equation. The angle measuring device isn't needed. No, when we're using a sextant for celestial navigation, we are using it to measure angles. We know the angles there. We don't know the distances. So we absolutely are triangulating. Yeah, 10th man, we're talking about sextant angles, not dish TV. Trilateration uses 3 towers or satellites, whatever you want to choose, doesn't matter. You can beg the question, don't really care. But those 3 or 4 or more satellites or ground-based towers, they are all, when using trilateration, they're all sending signals from the towers, from the 3, 4, 5 reference points, from those fixed locations. They're using signals and they're beaming them out. And wherever those signals meet, that's where your location is. When using celestial navigation in the sextant, it's the opposite. We are going from the observer outwards to the reference points. That's what you have to understand with triangulation versus trilateration. Trilateration is distances, known distances from the reference points like satellites and ground-based towers inwards towards the location of the person. It's the opposite with the sextant, with celestial navigation. You've got one reference point, that's you, where you are using the sextant. You have to measure the angles to the reference points like stars. So you're measuring things from the observer outwards to the stars. That's what the celestial navigation techniques do. Dave Christian says, get to the point. He wants to learn about what we've already wasted half an hour. Oh yeah, so I've wasted half an hour just absolutely debunking the claim that we use trilateration. No, we don't use trilateration. That's what I'm getting at. Dave Christensen, just tell me, do you understand that we're using triangulation here, not trilateration? So now let's get into how we actually use the sextant. So I've got a couple of screenshots here from an article called Celestial in a Nutshell. So this is going to be very interesting. How we're using the sextant here. Okay, the sextant. The mariner's sextant is a device for measuring angles. Yep. It is virtually the symbol of celestial navigation, and it is normally used at sea to measure the angles. There we go, measuring angles between the sun, moon, planets, and stars too, and the horizon. So between something like the celestial bodies and the horizon. But you can use it to measure any sort of angle. That's the first red box here I've got. Second one up, top right corner. There are two basic tricks when using the sextant. Getting the sun, the body that we'll use in this series. So they're talking about the sun and the horizon in your field of view. And being sure that when you measure the angles between the horizon and the sun, your sextant is vertical. If it's not vertical, you will not be measuring the true gap between the sun and the point of the horizon directly beneath it. Now we have to understand what we're seeing here when using the sextant. So we're using the sextant to measure an angle from the sun to the horizon. And look what it's saying right here. You're measuring the gap between the sun and the point of the horizon directly beneath it. What is that point on the horizon? That is going to be the GP of the sun on the horizon. Can you see where this is going, globe believers? What is the horizon in your globe model? It has to be a geometric edge, a physical geometric edge that is curving away at you, away from you in all directions. No, the black swan's absolutely debunked that. So we now know that when looking at the horizon, we're not looking at a curved surface. It's not a physical distance. But we know when using the sextant with celestial navigation, when looking at the horizon, we're looking at the GP point of the sun. Now you can see where this is going. When looking at the horizon, if you're seeing the GP point of the sun, that's the horizon. We're actually seeing thousands of miles. Let that sink in, globe believers. On your globe model, there is no way that you can see where the GP point of the sun is going to touch the Earth. But that's absolutely what we need to be doing when using the sextant. Here we go. This diagram here shows it perfectly. Figure 2, the angle measured with the sextant in reality is one corner of a right triangle formed by you, the celestial body, and its geographical position on Earth. Now, even though they've got that presupposition of a curve there, look how they're putting the angles. Look how they're putting this triangle. Yeah, from the observer here, it is a straight baseline to the GP. So you can disregard that curved surface altogether. When using the sextant, we are not making tangents to a globe, to a curved surface. There's no tangents going on here. Because if we were, the GP point would not be 90 degrees to the sun. We will not be directly looking at the GP point. And that's what the sextant relies on. Using the celestial body, measure an angle from the celestial body to the horizon. In this diagram, figure 2, are they using the horizon for a curved surface? No. They have to treat the horizon as if it was flat, as if the horizon was extending from the observer all the way out to the GP point. When using the sextant, we are physically measuring a geometric flat plane, as depicted in figure 2 here. Now they try and sneak in this presupposition of a curved surface, but it's not needed. So it's a right triangle formed by you, the celestial body, and its geographical position on Earth. A right triangle. Is a right triangle ever able to be put onto a curved surface? How are you going to put a right triangle? You can see there. They tried to put those two perpendicular lines, the red lines there, they tried to put that on the curved surface. They tried to end it at that curve. It's not going to be measuring an angle there, a 90-degree angle. You cannot derive an angle, let alone a 90-degree angle, to a curved surface. That's why they have to put these 3 straight lines. This is devastating for the globe. So the box in the right here, when you are taking a sight of the sun, you are one corner of a large triangle. Yep. So when you're taking the sight, there's a vertex there. You're one of the corners. It's a right triangle. There it is, a right triangle. Don't mention 90 degrees. That's what a right triangle uses, 90 degrees. Can't have it on a globe. It's a right triangle. The difference being that the bottom of this one is not a straight line but an arc. Here we go. Here's the presupposition. But in the figure, you need that straight line. You don't have that bendy line. Not available on a globe. And it's not just any old arc. This particular arc is the great circle track between you and the point of the Earth directly under the sun. A great circle. So enter the presupposition that we have a radius value. That's what you need. Yeah, you're presupposing that there is a great circle value beneath your feet, a curved surface beneath your feet. You're going to need an R value for that. And as we're going to go through using celestial navigation techniques, we're going to definitely disprove the radius of your presupposed spherical Earth. Like I said yesterday, the radius is never able to be derived in any circumstances. I'm challenging anyone to get the radius value of 3959 miles. That is the claim by the heliocentric model, that you have a radius of 3959 miles. And obviously Wally, he tried to derive the radius value. He tried to calculate it using satellites, didn't get anywhere near it, 2% off. Massive difference. You got like 38 something. It's 3959. Has anyone actually got 3959 miles? Because that's what the claim is for the heliocentric model. That's what you need to be calculating, 3959 miles. Our Bruni, he was off by a percentage. He didn't actually measure the radius of the globe. He was off by a percent. How are we getting the radius value when we're talking about a percentage error? To what? Who has actually ever measured the actual radius of this globe? You're getting a percentage error to something that doesn't exist, to something that has never been calculated. You're begging the question that you have the radius in the first instance. Let's go back to this. So a point known by the name geographical position is usually seen in the abbreviation GP. That's what we can see in the figure. Now, as you probably know, great circle arcs can be measured in degrees. And it's a happy fact that this bulgy bottom triangle, who's ever seen the bulgy bottom triangle before? The number of degrees in arc defined by the bulge is equal to the number of degrees at the angle at the top, where the sun is. Now, there's an interesting thing, isn't it? Yeah, if you think that you've got an arc beneath your feet, this is what they're claiming. That top angle here, where those 2 arrows are at the top, that vertex that's meeting at the sun, that angle there is going to be the same angle as the arc here on your presupposed spherical Earth. Isn't that interesting? Keep that in mind. Because this is a right triangle, the 2 acute angles add up to 90 degrees. And thus, the top angle is equal to 90 degrees minus the angle at your corner. So the angle that you measure with the sextant. So by taking the sextant shot of the sun and subtracting 90 degrees, you can find out how far you are from the point on Earth that is directly underneath the sun. Directly underneath the sun, you're going to need a right angle for that. That's what they just said. We're using right angle triangles here. But somehow trying to fit it into a curved surface does not work on a curved surface, does not work on a globe. So by taking this sextant shot of the sun and subtracting 90 degrees, you can find out how far you are from the point on Earth that is directly underneath the sun. Isn't it amazing what you can do with a couple of mirrors and a little trig? There it is, trigonometry. Yep, triangulation. Now, this next slide. This is where it gets interesting for the globe. Looks like I got my slides mixed up. I can't find this slide. All right, so, no, not that one yet. That's getting a bit too advanced. Not ready for that yet. And it looks like I haven't included the slide that says Oh, man. This is great. Alright, I'm gonna have to find this slide. Nope, didn't save it. Fantastic. So I'm gonna actually have to go to the actual website of this site, 'cause this is the devastating point for you globe believers. Gonna pull up the actual bear with me, it's gonna be worth it. Gonna stop sharing that. Go to a different tab. I'm gonna show you where this information is actually coming from. So share this screen. Alright, this is where the information is coming from. Make this a bit bigger. Everyone can go and Google this too. Got the address up there. Well, now I've totally lost it. Oh, this is a great live presentation. Thanks for sticking around, guys. When it comes to the killer point here. Alright. So, alright, this is the bit that didn't take the screenshot of. So here we go. The top of the triangle is 30 degrees, which means that you are 30 degrees on the great circle from the GP point of the Earth. So here we go. 1 degree equals 60 miles of arc and 60 nautical miles. So 1 nautical mile is 1 arc. 1 minute of arc on the great circle. So there's that claim again about the 60 nautical miles every degree. And isn't it interesting how they said you can find that arc angle right here? That arc angle is the same as the angle at the top here. So using that knowledge of 1 degree every 60 nautical miles or 69 statute miles, whatever you want to choose, we'll use nautical miles because that's what using in this article. So imagine if you're shooting an angle of 89 degrees. Yeah, so you've got an angle at the top of 1 degree. So 1 degree, obviously, you're going to be 60 nautical miles from the GP of the sun. So for every 1 degree is 60 nautical miles. And then maybe you can use this to derive a radius value. Do you think, globe believers? I haven't seen anyone try to do this yet. Yeah, obviously you can work backwards. You can go, what is it? So 1 degree is 60 nautical miles. So 360 degrees, if you're begging the question, you're on a globe. 360 degrees, that's going to be 21,600 miles for your circumference of your globe. So let's convert that. 21,600. What's that come out to for the circumference? 24,856. That is the circumference of your globe using this technique. 1 degree every 60 nautical miles. Comes out to a circumference of 24,856 miles. What is the actual circumference of Earth? 24,900 miles. So even using this technique, we can't get the radius of the Earth because we can't even get the circumference of the Earth. How are we ever measuring the radius of the Earth being 3959 miles? What is the actual radius of Earth? 3958.8. So 3959 miles. Yeah? But using that circumference that we've just derived, 1 degree every 60 nautical miles comes out 21,600 nautical miles, which is 24,856. So let's calculate the radius value using that. 24,856. How are we going to find the radius value? working backwards. So using the circumference, we can calculate the radius. So the radius is equal to the circumference divided by pi times 2. So obviously we've got this circumference of 24. This is what we've just calculated. If we're using 1 degree over 60 nautical miles, it comes out to 24,856 statute miles. So 24,856 divided by pi times 2. What do you think that comes out at? 3959 miles, do you think? No, 3955 miles. What's the radius of the globe? 3958 miles. Oh, but we're close, aren't we? We're close. No, you're still off. Has anyone actually calculated the radius of the Earth with using any observations here on Earth? Do you actually have a radius of your Earth? Why are we begging the question that we have calculated 3959 miles? Or 3958.8 miles? Where is that calculation? Where is anything that we've derived from Earth, from our observations? Where is the calculation that ever comes out at 3958 miles? It is not available to us. Maybe it's because of the equatorial bulge, do you think? 27 miles wider at the equator? Now this throws a bit of a spanner into the works, doesn't it? If you've got one radius of Earth being 3959 miles, what happens at the equator when you're 27 miles wider? So are you telling me, globe believers, that you can derive a radius value when you don't have one single radius value on your globe? It's an oblate spheroid, 27 miles wider at the equator than the poles. So why are we always told that we have a radius of your globe? That one has never been calculated or measured, begging the question. And two, it can never be calculated or measured because you do not have one radius. If it is an oblate spheroid, if you take a step, that is a different radius to your presupposed spherical Earth than when you took the step backwards. You keep traversing. If you're thinking you live on a globe, if you're begging the question, even if you're begging the question here, when you're traversing the globe, you've got a different radius at each and every point. So why is it, globers, that you think you can derive this single one radius value? You do not ever have one single radius value on a oblate spheroid. Are we getting it yet, globers? You do not have a radius. You do not have a radius to your globe. You do not have a globe. It's done. It's over right there. So let's go back to how we use a sextant. And this is what I'm going to be talking about tomorrow. I'm going to be hitting hard on the geometry factor when using a sextant, because we're definitely not measuring anything on a curved surface because it doesn't have a radius, doesn't have a fixed radius from the surface to the center of your globe. So when we're looking at the almanac, so back to trilateration, 15 degrees per hour amounts to 1 minute or 1 mile every 4 seconds. So the celestial bodies, when using the sextant, we're looking at the celestial bodies, they're moving 15 degrees per hour. That's the celestial bodies, not the Earth. Don't beg the question that the Earth's moving. All we see moving is the stars, and they're moving at 15 degrees per hour, which amounts to 1 mile every 4 seconds. So how are we ever using trilateration when we don't have even fixed distances to begin with? We've got moving targets here. Even if we are calculating the distance from the observer to the GP of that celestial body, it is changing every 4 seconds. You can't use trilateration. That's why we're using triangulation, because we never actually know the distances. It's because this book is made by astronomers, the almanac. We're talking about the almanac. This book is made by astronomers. And as astronomers don't talk about latitudes and longitudes, they do talk about hours and angles. So once again, if you think you're living on a globe, if you think that the sextant is measuring something like latitude and longitude, that's not what we're doing here. The sextant has nothing to do with latitude and longitude. The sextant is all to do about angles and declinations. Now there's an equivalent. A declination is the equivalent to latitude. And that's why we have something like a north value on the list of the almanac. But we're absolutely not talking about latitudes and longitudes. Because remember, the almanac is a book made by astronomers. They don't talk about latitudes and longitudes. They talk about hours, hour angles, and declinations, because that's what we use with the sextant. Nothing to do with latitude and longitude. Nothing to do with a globe. All to do with angles and declinations. And so when using the sextant, this is going to be the last point here before I'm going to be hitting this hard tomorrow. So there are some errors when using the sextant that you have to account for. One of the errors being here, the second thing that introduces an error of several minutes between the altitude of the sextant measure, the altitude the sextant measures, and the true altitude, is that in taking a site, you stand or sit some distance above the horizon. So when we're using the sextant, we're always above the surface, aren't we? Yeah, so we've always got an elevation, and that's what we need to account for. Now here it says we're actually looking down at it, but which increases the angle measured. So we've always got an increased angle when using the sextant above the surface of the Earth. We need to account for that. And how much depends on how far your eyes are above the surface of the water. So it's about 3 minutes for the height between about 9 foot and 12 foot, which equates to about 3 feet. Yeah, do the maths. And there is a table on the inside front cover of the almanac for this one, which incidentally is called dip, because dip increases the measured angle. It's subtracted from the sextant reading, so it's very, very important. When using the sextant, looking at the horizon, if you are anywhere above the surface of the Earth, you need to bring that measurement down to the surface of the Earth, and that's where it gets very, very devastating for the globe. You need to account for that dip angle. You need to account for your height above the surface of the Earth. Because remember that diagram at the start of this presentation? See the diagram? It's not a vertex. It's not an angle from the observer here. We have to put the angle on the surface of the Earth. And that's why this is the number one flat Earth proof. Because when using the sextant, we are measuring a flat baseline. And the flat baseline needs to be put on the surface of the Earth. The surface of the Earth is absolutely flat. That's what we're doing when using the sextant and when we're accounting for the dip angle, accounting for the height above the sea level. When we account for it, we put it on the surface of the Earth, and then it becomes a geometric measurement. This is the killer blow here. This is the number one flat Earth proof. We are physically measuring a geometric plane with the sextant. That straight flat baseline. Yeah, they try and put a little arc there, which would just disprove we don't have that arc. We don't have the radius value. On an oblate sphere, you do not have a radius value. You've got multiple radius values, none of which are ever derived from what we see here in reality. You're begging the question. But it's diagrams like this that necessitate that flat baseline from the observer. Well, actually, it's from where your observer's standing. That's what we need to make it. That's what we need to make these angles. That's what we need to put the baseline on. The surface of where you are standing. That's the dip correction. It becomes a purely geometric measurement. And that's the killer blow here. If you feel like the Earth turns on you, turn to Flat Earth School. It is around us 24/7 since the beginning of existence. We've just proven that here today. that we are living on a flat Earth. I hope you enjoyed this presentation today. It's obviously been very triggering for the trolls in chat. I appreciate everyone in there just swatting them away, patting them on the back saying, it's okay. Maybe you've got a globe in another life somewhere, in another imagination, because we don't have a globe here in reality. When using the sextant, we are measuring a physical geometric plane, and that's what we're going to be going at hard for the next couple of days. When accounting for the dip angle, we are putting this measurement from the sextant onto the surface of the Earth. Yeah, poor globers. Like I said, enjoy your flat Earth school. It is around us 24/7 since the beginning of existence. Thank you everyone for stopping by. This was triangulation using the sextant. Till next time, guys, go and experience, go and enjoy your flat Earth school.